Hey everybody. Alright, let's do an example with centripetal force. So let's say you're on a design team of a self-driving electric car. And kind of not joking, like before I was teaching at KCC, I worked as an engineer doing research and development of autonomous vehicles. And that was from 2003 to 2010. So kind of old news. This is not science fiction, right? This is an eventuality. It's just a matter of getting things safe and kind of affordable for it to be common. So let's say like there's a test track, and then it's like a banked road, like NASCAR, like a banked road like this. So let's say this is the top view. This is the like front view. Let's say you have the car going around the track like this way. So then the car is here going into the page. So let's say if you go really slow, like you come to a stop, what's going to happen? Like the car will want to slide down the ramp, right? Like if you just stop in the middle of the track, you'll slide down the ramp, which means you'll slide this way if you're going really slow. If you go really fast, other way around, right? If you're going really fast, you'll tend to run off the track, right? Like if you go too fast, off the track means this way, right? If you take a look at this, we're trying to turn left, but we can't. There's just not enough friction between the tires and the road, so you run off the track this way. So that means if you're going slow, you're falling down the ramp and friction has got to be this way. If you're going really fast, you tend to run off the track and friction is this way. So if we draw the free body diagram, I'll draw this view of it. What does it look like, right? The car has weight. I'll just say it like this, normal force. And then if you're going slow, you're going to slide down. So then friction is this way. And side to side, I mean, the friction is maintaining you from, right? It's keeping you on this path. So there's no motion side to side between the tires and the road laterally. So this is actually static friction. So this picture, this free body diagram is if you're going slow. And then other way around, like this way, if you're going fast. Okay. So let's maybe pick one of these. Let's say you're the one designing the car, and based on the radius of this track here, this radius, like you're driving on the freeway and there's an off-ramp, and so like the autonomous system can measure the radius of the off-ramp, and you know your own mass and you know the speed. So like how fast should you be going to not go running off the track? So let's pick this one to analyze. Okay, which way is centripetal? Because you're going in a circle, right? So if we look from the top view, centripetal is definitely toward the center of the circle here. Right, this way is centripetal. Which way is centripetal here on the front view? This way? That's not right, right? You're going in a circle. The circle looks like this, right? So centripetal is this way, right? This way centripetal. This way is centripetal. So how about I'll call that the x-axis. And then I'll just pick another axis. Okay, right, so I pick my coordinate axis so that it's in the centripetal direction, toward the center of the circle. Right, it's not this way. Centripetal is this way. Okay, and then let's take a look. Let's say if I have sensors in the vehicle to measure orientation, then I can measure this angle. And if I look at that picture, that angle is the same as this, which is the same as this. Okay, so now let's write Newton's second law decomposed. So in the x direction, I got that and that. So that's cosine, sine, and mass times acceleration. In the y direction, we have this, this, this. So n is positive and is adjacent, minus, and that's opposite, and there. Mass times acceleration. And because the car is going in a horizontal circle, there's no motion in y. X and z, yes, but nothing in y. Okay, and then we know at most the static friction is proportional to the normal force. Max, right? Actually, it's less than or equal to this, so then at most equal to this. Okay, so then we can substitute this here and here. I'll just do that right now. I'll just rewrite this equation and this equation. So the first one, Fs mu s n cosine theta. And one more thing, we know that this is centripetal. And centripetal v squared over that radius r. So I'll just write that right here, v squared over r. Okay, now let me write this equation. So n cosine minus mu s times n. Okay, so now we have these two equations. And let's take a look. Right, so like we don't know n, and let's say if you know the coefficient of static friction between the tires and the road, and you know the radius, then that means like your autonomous system can decide, I need to go no more than this fast, otherwise I'm going to run off the road. Right, so then you can solve for the speed. Can do, right? Just solve this for n, and then plug it in here, solve for v. Or, let's say you are designing the road. So then you say, okay, if I have a speed limit of 25 miles per hour, so then this is given. What should I choose as the radius of the off-ramp? Right, so then you kind of select parameters. And then as an assumption, as an engineer, I would say, let's assume the road is super slippery and there's no friction available. So you would just cross this out. I say, okay, there's no friction. And then you have your speed limit, say 25 miles per hour. Now I'll solve for the radius that you should choose as the off-ramp, right? And then solve for this. Okay, so give this a try. Give this problem a try, and let me know how it goes. I'll see you on the next video.